Welcome to another unit in this course on economics. This time I want to talk about policy multipliers. Policy multipliers, this means that if we have a model with exogenous and endogenous variables and we want to know which effects a change in an exogenous variable has on an endogenous variable, then we turn to policy multipliers. So what does this mean from a practical point of view? Usually if you work with the ISLM or the Mandel-Fleming model, then the variables determined via the model are GDP, the interest rate, or the exchange rate. So they are the endogenous variables. And our exogenous variables, so the information given from outside the model, that's usually the government expenditures, the money supply, this could be taxes, that could be the savings rate. So that's like the classical exogenous variables. And our idea would be to, for example, find out which effect does have a change in government expenditures on GDP, on interest rates, or something like this. And that's where we use our policy multipliers for this. And well, we can start all of this with a very easy first example. And with the easiest of models, that's simply the idea that we start with the expenditure equation. We solve the expenditure equation for GDP. So we insert for consumption the consumption function. We solve this for GDP. Then we get this result as given here. And now we can ask what actually happens in this very easy model, which only consists of the goods market, if government increases their expenditures. So what happens if the part G, the government expenditures, actually increase, let's say by DG units? Well, in this case, we simply replace G with G plus DG. It will look like this. And then we can actually pull the DG out of the brackets, giving us two parts here. The first part, which is the original one, and that's actually the effect. So here we see for DG unit increase in government expenditures, GDP will increase by DG divided by S units. Well, that's one way to go about this. However, we might also have a different approach, a more structured, more mathematical approach to solve the same problem. And for this, we simply consider the equation again and just slightly reformulate the question. And that's basically by asking by how many units does the dependent variable y increase or change if G is increased by 1 unit. So here we're only talking about 1 unit changes. Because the advantage of asking this question is nothing else than the derivative of y for the variable G. So we simply take this equation, same thing here, and we get the first derivative of this function for G. So we derive y for G. This gives us the multiplier dy by dg. That's actually the government expenditure multiplier. Which effect does government spending have on GDP? And the answer is 1 divided by the savings rate. So if government expenditure is increased by 1 unit, so let's say by €1, then GDP is increased by 1 divided by S euros. So if we have a savings rate of, let's say, 20%, so S is 0.2, then this factor is 1 divided by 0.2, so this factor is 5. So for each unit the government spends, GDP will increase by 5 units. €1 spent, GDP increases by 5 euros in total. Well, that's the first easy version that can also give us a short answer if we only consider the goods market, what the effects of government expenditures are. However, we can also use this to answer a different question or talk about a different context. And that's the idea of what happens if the savings rate increases. So if people actually save more money and consume less, therefore. Well, in this case, we use the same formula we had before and simply derive this formula for S. So in this context, we get this derivative due to the fact that the S here is in the denominator. We get a minus in front. Everything on top here is positive. S squared is also positive, or 0, but well, we are not allowed to divide by 0, so we assume this is also positive. Positive divided by positive is positive, but with a minus sign means this multiplier, independent of what the different variables are, is always negative. So if this is always negative, this means an increase of the savings rate will always have a negative effect on GDP. Well, there's a name for this. This is referred to as the savings paradoxon. This says if you save more, GDP, income, will decrease. That's like the mathematical proof, via the idea again of policy multipliers, the mathematical proof for this savings paradoxon. Well, that's a second different approach for using the idea of policy multipliers. However, we can formulate this in a more general fashion, because in this context, we only worked for the goods market. So the question is, what happens if we have a more sophisticated model, like even the ISLM model has goods market and money market. But we could use the Mandel-Fleming model as well. In this case, we would also have the foreign exchange market we would have to consider. Or we could include financial markets, labor markets, and so forth. So if you have a more sophisticated multi-equation model, it's the best idea, if you're interested in some kind of multipliers, to use a specific scheme. And well, here in this context, start by considering all equations you have in your model and get the total differential of all of the relevant equations, considering all endogenous variables and all relevant exogenous variables. If you have some exogenous variables which, however, are not of interest to you, well, you can skip them in the context of this total differential, meaning we are holding them constant. But here you should consider all endogenous and all relevant exogenous variables. Then write the resulting system of equations in matrix form and order this. Order this in a way that on the left side you have all the endogenous variables, here meaning all derivatives for GDP, interest rate, exchange rate, and on the right side is everything else. Then basically the left side should look like you have a matrix times a vector of dy, di, de. On the right side, there's also a matrix, now with a vector as well, considering, for example, dm money supply, dP, price level, dy star, so foreign GDP, dg for government expenditures. Depends which exogenous variables you deem important. If you have arranged it in this fashion, what you can do next is on the right side, consider only those differentials which you really need in the calculation of the multipliers. That's what meant with factoring out all differentials. So we actually have on the left side matrix times vector, on the right side matrix times vector. And then in this fourth step, we are considering only the matrix on the left side, which we call the system matrix, and we calculate the determinant of this left-hand side system matrix. That's called then the system determinant. That was the matrix for all the endogenous variables. Once we have this, we only need one additional step, and in this step we are setting all of here the exogenous variables, the exogenous differentials, equal to 0, which we don't need. So there will only be one vector left on the right hand side. That's the vector relating to the exogenous variable we are considering at the moment. If we have this, we divide by the corresponding differential, and then we simply have only one vector left on the right hand side. And this means we have a matrix times the solution vector on the left. The solution vector, due to the fact that, for example, if we are interested in effects of dg and we divided the right hand side by dg, we get dy by dg, di by dg, de by dg. On the right hand side, we only have the vector, in this context then if we work with dg, relating to dg. Well, what are we going to do next? At this point, we have a classical system of linear equations, which we can solve in different fashions, for example with the Gauss algorithm, or even though it's not as mathematically sound or efficient, a good idea, especially if you're only interested in one or two of the parameters, is, for example, the Cramer rule. Because using the Cramer rule, you can solve for one of the solution variables by itself without having to calculate the solutions for all variables at once. So this is actually a neat tool to use here, which, however, I'm not going to go into more detail in this course. Well, once you have this solution, you actually have calculated the corresponding policy multiplier. Well, that's then basically everything there is to be done to get from any model your policy multiplier by deciding which endogenous variables you have in the model, which exogenous variables are important for you, which effects you actually want to consider regarding your endogenous variables, and then simply reformulating all of this that it looks like a normal linear system of equations and solving this with a suitable approach algorithm for linear systems of equations. Well, as I said, that's basically it. So I hope you enjoyed listening to this unit, and I say goodbye and see you next time.